Not satisfied.
So let's think of let's say we have R2 and we have a quadrant like x-axis, y-axis, right? So if we take the first quadrant and the third quadrant, Q1 and Q3, right? So essentially we are taking kind of half, right? The other Q2 and Q4 we are ignoring, right? So will this qualify as a subspace? So if I look at the additive property, if I add any two vectors from any of these, will the resultant be, I'm just thinking if anything will end up in Q2, because that's the only concern I have. Negativity, like scalar multiplication, that will be easy. If you multiply Q1, it will end up in Q3 and vice versa. Definitely origin is content. So third property is pretty much sure shot. Only the first one, we take two vectors. Yeah, probably the y-axis and x-axis, right? So it will end up in Q2. Yeah, it's difficult.
Okay. Can anyone tell me, is the S1 a subspace or not? People said yes. I want a reason for that. I just want a reason for that. Is S1 a subspace? Anyone? Can you quickly unmute yourselves and just maybe tell me Ravikant, Shriram, Praneeth, Chittu Raja, Nagashri, Bharat, Anurag, Aditi? Anyone?
Okay, so all all subspaces that are less than r per n Rn are subspaces of the.
No, I don't know Rn. I don't know Rn.
Okay, then
I don't know any Rn. I only know S1. I haven't met Rn yet.
Let's go step by step, right?
Hmm.
Why is S1 a subspace? That's all we're asking. We're not asking. I mean,
because it
we
size
just have to
closure addition and
exactly.
closure multiplication, and it even contains the zero vector. That's why it's a
It
subspace.
satisfies all three properties, right? Because if I take 0, 0 and I add it to itself, which is my voice clear?
Yeah. Perfect.
Yeah. This is also equal to 0, 0. And we know 0, 0 belongs to S1, right?
Right, guys? So it satisfies the uh, closure under under addition property. And what if I multiply some scalar quantity with 0, 0? What happens then? What happens then if I multiply some scalar quantity with 0, 0? I'll get 0, 0, right? And since it is origin, it's part of the subspace. Origin itself is the only element in the subspace. So S1, I think I can safely say is a subspace, right? I can safely say it's a subspace. But now Vinay is very concerned. He is very concerned about all the other points. He does not want to neglect the other points. Okay, so he has this favorite point of his 1, comma 2. He wants to add this to a subspace. Can he call this a subspace? A set containing only 1, comma 2. He likes 1, comma 2. He thinks it's very special. Okay. He thinks it can qualify as a subspace. Can anyone tell me, does it qualify as a subspace?
I had a small doubt. Shouldn't every subspace contain the zero vector?
Yeah, it should. It should. Right. Right. So can we call this a subspace now? Can we call S2 as subspace, Nagashi?
No, I don't think so.
Right. Right. It does not even include the origin, right? We cannot call it a subspace. So Vinay, sorry to say this, but it's not really that special. So we will have to include 0, comma 0 to it. Not going to work out, mate. Anyway, so let's take another example. Now we'll include the origin. Okay, now we'll include this origin to this. I don't want winner to feel bad. I want him to feel good about this special point of his 1, 2. Let's include 0, 0 in the subspace.
Can we try to say that S3 is also not a subspace once, maybe?
Okay, S3. Oh, we haven't. Okay, we'll come to S3 as well. We'll come to S3.
Okay.
It's still pretty ahead.
Yeah, okay.
So
So this is not a subspace. Okay. Okay.
yeah. So we have S3 that has two elements, 0, 0 and win is special point. Okay. So can Vinay call this a subspace now? Can anyone just tell Vinay that? Can he call this a subspace? Anyone? Can we call this a subspace? Shriram says S. I don't know what that means, Shriram. I don't speak alphabets.
So it violates the scalar multiplication, right? If I multiply by 2,
If
But-
do the scalar multiplication, shouldn't that vector as well belong to the same vector space?
True, true, true. Right. Okay, Devasmith sir said the same thing, and Nagashri pointed out the same thing. And also, so first of all, let's check for the origin. Does this set has the origin? Yes, it does have its origin. Does it satisfy vector addition? So if I take two vectors from this set, that is 1, 2 and 1, 2, and add those two vectors, will I get the resultant vector in the subspace? So 1, 2 plus 1, 2 gives me Vinay, can you write that down? 1, 2 plus 1, 2. Right. So it gives me what? 2, 4. Right? Is 2, 4 part of this set? Guys, this should be pretty easy. Okay. I mean, I am expecting a lot of answers for this question at least.
Does not.
It's not right. So it does not satisfy vector addition. I see. What about vector multiplication? Although I need not need to concern myself with that. Need not concern myself with that. But let's check. Does it satisfy the scalar multiplication? Does it even satisfy the scalar multiplication? So if I multiply say 2 or say 3 with 1, 2, will it give me a vector in the subspace or subset? We haven't qualified it as a subspace yet, so we'll call it a subset. Scalar multiplication. 3 times 1, 2.
Does not belong to because 3, 6.
Yeah, 3, 6 does not belong to the S3. So we can safely say this is not a subspace. Sorry again, mate. Not a subspace again. We'll have to take a break for a couple of seconds. Our computer G is actually attending to a very important call. Both lies on the vector. Yes. So anyway, we've seen that okay, this is not a vector space, right? What can I do to make it a vector space? What can I do to make it a vector space? I want Vinay to be happy, okay? I want him to be happy about his special point. So what can I do to make him happy? Apart from obviously gifting him a Rolls Royce, but what else can I do to make him happy? How can I make this a subspace? Vinay is adamant. He wants this 1, 2. That's why he hasn't changed this point till now. He wants this 1, 2 be the part of the subspace. Okay. What can I do to make him happy? See, Vinay, will you be happy if I gift you a Rolls Royce? See, I told you guys, right? He'll be happy. I know he'll be happy. But can I also make him happy by just converting this to a subspace? So, can anyone tell me how can I convert this to a subspace? So this fails two conditions. If I satisfy these two conditions, I can make Vinay happy. I can make him happy about this special point
You
of
draw a line from origin to that point and then kind of extend it, right? So that way, it will satisfy the third property, origin is involved.
right.
And then scalar multiplications and any linear combination will also lie on the same line.
Right. So,
Right.
sir, can I say that 0, 0 should be part of the subset, and any scalar multiple of 1, 2 should also be part of the subset,
Yeah.
right? Okay. So, can I call this a subspace now, guys? Can Vinay now be satisfied? Can he be happy now, finally? Guys? Anyone?
It gets the stick now. This line.
Yes. Yes.
So, can Shriram, can you tell me why can I call this a subspace? See,
Because
he wrote down on bold. Yeah, go ahead.
all linear combinations of the points here are satisfied, right?
Okay, I know. I'm not. I don't know what linear combination is.
Okay, so but you talked about it in the first condition, right?
I forgot. I forgot everything.
Okay, fine. So when you add two vectors in that subspace, you get another point in the same place. So that is same subspace.
Hmm.
So
Okay.
that is that's rule is getting satisfied here, right?
Mm-hmm.
So and the origin is also there in the
Mm-hmm.
subspace.
Right.
And also that all obviously you know that origin, anything multiplied with the origin is in the origin. So the other point also you have the scale. If you multiply any scalar to another point, you are again getting another point in the subspace because you have an alpha.
Right.
So you satisfy all the three conditions, making it a subspace.
Correct. Correct. That is correct. So Vinay has already written everything. He's quite happy that we have satisfied him finally. It is a subspace. Congratulations, Vinay. Okay, so we have 1, 2 and 3, 6. Those both are part of this subspace subset. And the addition of that is 4, 8 is also part of the subset. And if we multiply it with some scalar quantity, okay, that also is part of that subset. So we can finally call this as a subspace. We can finally call this as a subspace. Okay. Okay, now okay, Maria has texted me. Maria says that I'm not happy that Vinay included his favorite point. Maria wants to include her favorite point as well. Can you tell us your favorite point, Maria?
Okay, when did that happen? Okay, 5, 12.
Okay, 5, 12. It just happened. You forgot about it. So we have another point. Okay, Vinay's points are still there, but Maria has included her favorite point, 5, 12. Okay. Can I call that a subspace now? Can I call a subset including 0, 0, alpha times of 1, 2 and 5, 12? Can I call this a subspace? Anyone?
No, because scalar again, any scalar multiplication of 5, 12
Right,
not
right.
be there in that
Correct,
S.
correct. So if any scalar multiplication with 5 comma 12 will not be part of that. So Vinay has included that now. Vinay says that okay, I'll multiply some scalar quantity with it. Okay, he has multiplied it with some scalar quantity called beta. Okay. Now tell me, can I call this a subspace? Can I call this a subspace? See, Maria wants to include her point as well. Okay. We can't just make Vinay happy. We have to make Maria happy as well. So just tell me, can I call this a subspace now? Anyone? Aditi, Praneeth, Anurag, Bharat, Chittu Raja, Nagashri, Ravi.
It won't be a subspace, right?
Why?
Because if we add those two linear combination of those two, like
I don't know what linear combination is,
okay,
Praneeth.
let's take alpha as one and beta as one. Then if we add both the vectors, then we get a vector 6 and 14, which is not uh in these 3 points.
Right, right, right. So if I take my vector 1 comma 2 and my vector 5 comma 12, I get 6 comma 14, which is not part of this subset. Okay. This is not part of the subset. Origin is part of it. Vector addition does not satisfy. What if I do scalar multiplication? It will satisfy because you multiply anything with 0, it will give you 0. Alpha times of 1 comma 2 is already part of it, and beta times of 5 comma 12 is already part of it. It just does not satisfy one condition. That is vector addition. How can I now make both Maria and Shrivane happy together? I want to call this a subspace. I can't. What changes can I make to this? What changes can I make that to that? Anyone?
Maybe let's add that to the
Vectors, Maria, vectors.
sorry. Yeah, yeah, so initially when we had S4, we actually got a like maybe you can tell them what it geometrically means too. Like you have a set of two lines, right?
Yeah, we'll go to GeoGebra after this. We'll go to
Okay, okay.
GeoGebra. See, guys, Maria is not happy with you. She wants you to interact a bit more. Please help me out. How can I make this a subspace? That's my question. That's it. It only satisfied 2 out of 3 conditions. I want it to satisfy the third condition as well. What should I do? Chittu Raja says second plus third. Can anyone elaborate on that a bit more? That's the answer, but I want someone to elaborate on that a bit more.
So if this subset is not satisfying the scalar addition, then why don't we just add the second one with that vector?
Oh, that's really nice idea. That's really nice idea. Let's try it out. Let's try it out. Let's create a subspace or subset S6, which has 0 comma 0, alpha times 1 comma 2, beta times 5 comma 12. Sorry, I almost forgot Maria's favorite point. Sorry for that, Maria. Beta times 5 comma 12 and alpha times 1 comma 2 plus beta times 5 comma 12. So can I call this a subspace now? That's my question. Guys, Chittu Raja says yes. Praneeth says yes. Why?
Any linear combination would belong to that.
I don't know linear combinations, Nagashri. Sorry.
Both vector that is written is a linear combination, right?
Okay, if you want, I can define what a linear combination is, but we haven't defined linear combination yet. So that's why I'm not using the term. Maybe you can rephrase the same thing, say it in some other way.
You take in the set of real numbers,
Hmm.
that whatever combination addition you get after doing the scalar multiplication separately, it would still belong to the same set, therefore it would satisfy.
Correct. So origin is satisfied, scalar multiplication is satisfied since we have taken alpha times 1 comma 2, beta times 5 comma 12. And vector addition is also satisfied because this alpha times 1 comma 2 plus beta times 5 comma 12 actually satisfies all the previous properties, everything that we have written before this. Okay, it takes into account all the vectors in R2. This alpha times 1 comma 2 plus beta times 5 comma 12.
Wouldn't alpha 1 comma 2 plus beta of 5 comma 12 also include 0 comma 0 and
Yeah,
everything?
that's why I said that it satisfies all the previous conditions.
Okay.
So 0 comma 0 it satisfies, alpha times 1 comma 2 is satisfies, beta times 5 comma 12 it satisfies. So if we put both alpha and beta equals to 0, it gives me 0 comma 0. If I only put beta equals to 0, it gives me alpha times 1 comma 2. If I only put alpha equals to 0, it gives me beta times 5 comma 12. And if I take any point from those two lines, alpha times 1 comma 2 and beta times 5 comma 12, and add those two, I can get all those points by just addition. And this is very special thing we did here. This is very special. Okay, this alpha times some vector plus beta times some another vector is very important, very special. Can we write it down, Vinay? Can we write this down? Alpha times of u plus beta times of v. Yeah. So this is actually what we call a linear combination of two vectors. A linear combination only means that it satisfies both vector addition and scalar multiplication. Since you can see that we are multiplying some scalar quantity, at the same time we are adding those two vectors as well. Okay, so it satisfies both those conditions. And if you keep these alpha and beta as 0, it gives you the origin, so it satisfies the third condition as well. This is very special. This is called a linear combination of two vectors, u and v. Okay, so now we have discussed that. Now we have discussed what are subspaces. Let's get a visual idea of this. Let's get a visual idea of it. Vinay, can we open GeoGebra? Can we start with a point in? Okay.
Do you want to see S1, S2, S3, S4,
Yeah,
S5?
yeah. So we'll trace everything. We'll see what's happening. So see, right now this is just the plane R2. I have my point 0 comma 0. We saw that it satisfy all the conditions, right? I can call my 0 comma 0 a subspace in R2. Okay, but what happens if I see when I is showing you what happens if I multiply something to this? It gives me 0 comma 0 again. It satisfies the vector multiplication, scalar multiplication. What happens if I add something to it? Right? So it gives me again the same thing. Right? It gives me 0 comma 0. You add any number of elements from this, it gives you the same point. So it is a vector space. It is a vector space. It is a subspace of a vector space. Okay. Now, Vinay wanted to include his point 1, comma 2 in the subset 1, comma 2. Maybe make it as a vector, Vinay. Vector 1, comma 2. Yeah. But we observed that if we add something to 1, comma 2, say we add 1, comma 2 to 1, comma 2, we get 2, comma 4, which was not a part of the subset. So what we did was we said, okay, we'll multiply it with some scalar quantity so that we get everything that's, so see, can you see, we multiplied 2 with 1, comma 2, we got 2, comma 4. That does not lie in the subset of that only includes 1, comma 2, right? So instead we said, okay, what we will do is we will multiply it with a scalar quantity so that it includes all possible points. Can you trace it? Trace it. So now what we are doing is we are showing you that what happens when you multiply some scalar quantity. What is the object that you get? Can you all look at it? That what's happening when we multiply some scalar quantity with our vector 1, comma 2? What are we getting here? Anyone? Guys? Ravi, Praneeth, Shriram, infinite line. Yeah, right. We are getting a line. We are getting a line y equals to 2x, right? That's the line we are getting. And if we take any point from this, any vector from this line, we will get another vector on this same line again. So say I want 1, comma 2 and I want 2, comma 4 and I want to add those two, 1, comma 2 plus 2, comma 4. Okay, what will I get if I add 1, comma 2 and 2, comma 4? You'll have to define it when I first, I think. Define the vector. Oh, tuple. Okay. Yeah, right. So I added a vector 1, comma 2 with another vector 2, comma 4. Can you see that I got a resultant vector that is 3, comma 6 and that lies on this line? So it is a subspace in itself. This line is a subspace in itself. Now what happens when we include Maria's favorite point in this 5, comma 12? What happens then? Guys, what happens when we include 5, comma 12 with this? Does that lie on this in this subspace? Does that lie on this in this sub? Nishan says no. Okay, Nishan says no. I believe Nishan. Okay, I trust him. So it does not lie on this subspace, right? Okay, then we said, okay, let's think about it. If we want to include 5, comma 12, we must also include all the scalar multiples of that, first of all, right? We must include all the scalar multiples of that. So if we multiply 5, comma 12 with say B or A, we will get another line. Can you trace that also, Vinay? Yeah, we will get another line. Okay, but what happens if I take any vector from this line and add it to a vector from the line y equals to 2x? Will that lie on either of these lines? Will that lie on either of these two lines? So I got a vector C. C is a vector. You'll have to show the negative side, Vinay. Third quadrant. Chittu Raja says no, not necessarily. Right. Can you see the C line? C vector. We got the C vector. Can you see that it's not lying on the line of vector W? Go ahead, Nagashri.
Yes.
You were saying something.
No.
Okay. So Dilchasp says Nishan. Right, Nishan. This is very Dilchasp. And so it does not lie on the either of these lines, right? Now what should I do? So what we said was we'll add these two. We'll add these two C to see if we get, now we'll verify it. Okay. We just threw it in the air that okay, we'll get all the points. Nobody even asked me why would we get all the points? Nobody even questioned me that. Everybody believed me. All are gullible. Okay, I can tell you all guys that okay, I am the president of United States. You'll all believe me. Although I don't look like him, but yeah. So all are gullible. Nobody questioned me there. Now we'll see if we will actually get a point on this R2 or not if we add these two vectors. So alpha times of say 1 comma 2 and beta times of 5 comma 2. If I add those two, will I get every point on R2? So can we take the linear combination, Vinay?
Yeah, 1 second. So you want the linear combination?
Of the two vectors. 1 comma 2 and 5 comma 2. You can create another variables. Just create another variable. One.
E plus
No. D, not
W,
D
right?
plus. You'll have to multiply it with variables as well.
Yeah, W is A times V,
Yeah.
and D is B times U.
Okay. Yeah. Perfect.
Or
D plus
okay,
D plus W. So can you add these two?
yeah.
W plus D.
I'll just do A times U plus B times U. That's
Yeah,
okay.
that works as well. So we got a resultant vector E. Can you change the color for E, Vinay, so that it stands out and hide everything else maybe. Yeah. So guys, you're pretty gullible, okay? Now I'm actually helping you out to see if I was telling you the truth or not. You all believed me blindly. Now we'll see if I am a liar or not. Okay. Okay, Vinay has started weighing these values. We'll see what we get. Okay, Chitturaja says we trust you. Thank you, Chitturaja. Somebody does. Okay. Thank you. I much appreciate it. So can
1 second.
anyone tell me what's okay? Why are we can you what are you tracing, Vinay?
A times U plus B times V.
Can you see if you're tracing it? Can you click on that? No, you are not tracing it, Vinay. Are you okay? You're tracing it. Okay, can you delete this these whatever is unnecessary from here and just do it fresh? Just delete everything that's unnecessary. We only need two vectors. We'll create the free variables as well. Delete everything except the two vectors. We don't need anything.
Yeah, let me just do it.
No issues. So we have A and B already. You just need to define the vectors 1 comma 2 and 5 comma 12. 1 comma 2 and 5 comma 12. 5 comma 12. Keep the result, change the color of the resultant vector, okay? So that
Yeah.
we can differentiate it. And show the trace. Perfect. Okay. Now, when I will actually vary the values for A and B, tell me what do you observe here? Can you change the speed of those as well, Vinay? For make it faster. Yeah. Can anyone tell me what are we observing here? Earlier we were getting a line. What are we getting now? What are we observing here? Anyone? Ravi, Praneeth, Nagashri, Chitturaja, Bharat, Anurag, Aditi. Plane. Oh, right. We are getting a plane now. And with this plane, if we vary the value of A and B, can we reach all the points on R2? Can we reach all the points in R2? Maybe can you increase the steps for these variables? Vinay? Just make them 100. Instead of 10, make them 100. Let's see. If we increase the value of A and B, let's see what happens. Okay. Now we are varying these. Just increase the speed for those. Vinay.
Oh God. Okay.
Else we won't be able to show it properly. Increase the speed.
It's skipping a lot of points in between them.
Okay. So can you look at it that if we increase the value for A and B, we can actually reach almost, or not almost, we can reach every point on R2. So guys, I wasn't lying to you, okay? You can trust me. I'm pretty trustable.
No, I think the better way to think about it is, um, let's take this blue vector over here, right? The one I'm pointing on. If we have to add, if we were able to reach that one vector, right? If I just increase the value of alpha beta by 2, I would be able to reach 2 times that vector, right?
Right.
If I increase the value of alpha beta by 3, I would be able to reach 3 times that vector. So if you're able to reach this one vector in this direction, you'll actually be able to reach the entire line passing through 0, 0 and that point, right? Because you can just scale the values of your alpha and beta respectively. In the same sense, if you're able to reach every direction, I feel that's what we only need to check, right?
Right.
Instead of checking all the possible values, which will actually give you all the possible directions, if it is able to reach one particular direction, you can actually reach the entire line passing through that. So in essence, you just need to check whether it can go from 0 degrees to 180 degrees, because then on the other side, you'll just
Yeah,
have.
negative, like, yeah.
Exactly.
So I don't think I could have explained that better than Vinay. So do you guys have any doubt till this point? Anyone? Any doubts? We started with the idea of vector
This is,
space. Yeah, go ahead, Maria.
yeah, this visualization is actually like when you're first introduced to the idea of like like when you have vectors and you like want to know what a subspace. It's this visualization is like really a really nice way to get introduced to it.
Right.
I feel like this is the way we should have learned it. I mean, it gives you way more how you're able to reach every vector in R2 using this. Like this visualization is really nice, even when I was introduced to it the first time.
I'm hoping the others are finding this interesting as well. So I I yeah, okay, Chittura is true. So we have yes. So people agree. Okay. So I hope that it's clear to everyone what we have done till this point. We have discussed what we will discuss the idea of a vector space. Afterwards, we discuss a subset of a vector space that satisfy all the properties that a vector space satisfies. That is the subspace. Okay. We saw how Vinay, can you share the GeoGebra?
Okay.
So then afterwards, we saw that how can we even think of subspaces from the very basics, from the very conditions. We started with the conditions, right? We included 0, comma 0, the origin, and we build on that. We build slowly on that, and we got subspaces in R, right? Started with vector spaces, discuss subspaces. Started from the bottom, here we are. So now let's discuss one very important thing. Can anyone tell me what are the what are the subspaces of R2? Now we have discussed that, okay? We have discussed that. Keep that in mind. I just want you to name all the possible subspaces of R2. Or have we discussed all? Have we missed anything? You can also tell me that. See, don't trust me blindly, okay? You can count a question. So tell me, what are the possible subspaces of R2? Guys? Anyone? What are the possible subspaces of R2? Chituraja says plane passing through origin, line passing through origin, and origin itself, right? So we have the origin. That's what we started with, right? That's what we started with, or the origin. That's the first part of what one such subspace. You missed null set. Null set is just a set of vectors, Aditi, from the R2. So we haven't discussed the concept of null set yet, but yeah, null set is nothing special. It's nothing special. It just satisfy a particular condition. It is just like other vectors. It's like other subspaces. In fact, it is one of the subspaces in R2. Okay, we'll be coming to we'll be discussing null set. So we started with the origin. Okay, then we included Vinay's favorite point. I mean, it's also subspace of R. Yes, yes, yes. It is a subspace. Right.
Yeah, I mean, someone actually mentioned lines passing through the origin,
Right.
right?
So
So
it includes all.
yeah, null space would be something that we've already mentioned. Yeah.
Correct. So we started with the origin. Then we included Vinay's favorite point, and we figured out we can't only include that. We'll have to include all the multiples of that as well. And those multiples gave me a line. Okay. Then Maria said, okay, I want to include my point as well. We observed that we have to include all the multiples of that as well. So we observed in general that after origin, all the lines passing through the origin will also be subspaces in themselves. So first origin, then all the lines passing through the origin. Then we observe that we can't, if we take two of those lines, we can't call them the subspace. Individually, we call them, we can call those lines subspaces. But if we take two of those lines, we cannot call them subspaces. We have to include their addition as well. That we call linear combination. Okay. So we figured out after we take linear combination, we get an entire plane, and that entire plane spans the entire R2. We get the entire R2 by that. So origin, all the lines passing through the origin and entire R2 plane. So these are the possible subspaces of R2. Okay. So I hope this part is clear to everyone. We discussed from the basics. We built everything till this point. Now can we move on to the next question? Yeah. So given a vector 1 comma 7, what does alpha times 1 comma 7 represent? Is it a subspace of R2? We have discussed this. Can anyone answer this? We've already discussed it when we were discussing the subspace. Can anyone tell me this? Is this a subspace?
Alpha, if alpha equal to 0, then contains origin.
Yeah, I think one point note to mention, like we can mention is, see, we built it up like this 0, 0, alpha times 1, 2. But remember that when we did alpha times 1, 2 itself, if alpha were to be 0, it would actually include this point. So when we increase that subspace from S1 to have only 0, 0, and we increased it to 0, 0, comma alpha 1, 2, I didn't have to write 0, 0 specifically because alpha 1, 2 also subsumes 0, 0. And similar to what Chetan explained, I think here, when we say alpha times 1, 2 plus beta times phi 12, it actually includes 0, 0 as well, alpha 1, 2 as well, beta phi 12 as well, and also all points that are the
Linear combinations.
linear combinations of these 2 points. Yeah. Because alpha 0, 0 gives us 0, 0, beta of 0 gives us alpha of 1, comma 2, and alpha of 0 gives you beta of 5, comma 12. And changing all, taking all combinations will result in all the other points of R2.
Okay, Aditi says null set does not make a subspace of R2 because of origin condition. Yes, yes. Right. So if you have nothing in your set, that's not a subspace because you don't have the origin. Thank you, Aditi, for pointing that out. I thought you were talking about null space.
Yeah, even I was talking about
Yeah.
I thought she was talking about null space.
Yeah, right.
Okay.
Sorry for that, guys.
Null set just means an empty set, isn't that what
Yeah,
she
right.
means?
Null set is an empty set. I was thinking of null space. I'm sorry for that, Aditi. You rightly pointed that out. So if we have, say, an empty set, okay, that does not have any elements in that we cannot call that a subspace because first of all, it fails the first condition. It does not have origin. Secondly, there are no elements to add, so you can't even talk about the vector addition. Then you can't talk about scalar multiplication because you don't have any elements.
There is no vector at all.
Right. You don't have anything in that. So let's just look at the next question. That was 1 comma 7 and a set containing alpha times 1 comma 7. Is that a subspace? Can anyone tell me that? Alpha times of 1 comma 7, is that a subspace? Anyone?
What if my point, my favorite point was 1, comma 7, or maybe
One
Bharat's
crore.
favorite point was 1, comma 7.
You
We could have
forgot
done the
your
same
favorite
thing,
point.
right?
Okay,
We could have done the same thing, right?
this
Yeah.
is actually Nishan's favorite point. Okay, 1 comma 7. And Bharat's as well. Bharat's okay. We have two people liking the same point. Okay, guys. So can you guys make both of them happy by saying, is this a subspace or not? Anyone? Praneeth, Ravi, Nagashri, Chittu Raja, Anurag, Aditi is here, Rishabh.
We already discussed, right? So any multiplication of 1 and 7 will be essentially going from origin to that, and then any kind of, so essentially it will become a line passing to the origin.
Correct.
So that's
So,
another way to think about alpha into any kind of.
right. So Rishabh also says yes, that it is a subspace. And since if we put alpha,
Okay, it will give me the origin, and if I put uh, alpha equals to some scalar quantity other than 0, it will give me all the possible multiples of the vector 1 comma 7. Additionally, if I take any vector on this line, okay, and I add those two vectors, I will get the resultant vector that lies on the same line. Okay, so we can call it a subspace. Can we take a look at the next question, Vinay?
One second.
Yeah. So the next question says a subset, is R3 a vector space? Is R3 a vector space there? Interesting. We were only talking about R2. We didn't talk about R3. Now, sir has asked us, what is R3 a vector space? Okay. So, oh, Ravi says yes. Ravi, you'll have to elaborate more. I don't. Yes, we can have vectors in R3 as well. Yeah, we can have vectors in R3, but is R3 a vector space? Just because a set has some vectors in it does not satisfy the condition for a vector space, right? Is R3 a vector space? Let's only talk about the three conditions we were focusing on, because the rest are not that important when we talk about these nice vector spaces. So
If you add any two vectors in R3, it still belongs to the vector space. I mean, it still belongs to that space itself.
correct.
And
And
multiplication, it still stays in the same set.
okay.
It's closed under addition and multiplication.
And does it have the third condition satisfied? Does it satisfy the third condition as well, Arish? Does it have an origin?
Yes, 0, 0, 0, right?
Right. So we can call it a vector space because it, first of all, it includes the origin. Secondly, it satisfies the vector addition. You take any two vectors in R3, the resultant vector is going to lie on R3. You cannot give me any example of two vectors in R3 when added give you vector in some other dimension. You cannot give me any such example. Two vectors from R3. Yeah, go ahead, Nishan.
Are all planes in R3 a vector subspace of R3?
Oh, we haven't even considered that it is a vector space. We haven't even talked about that. We are not even convinced that it is a vector space. Once we consider it a vector space, only then we can talk about subspaces.
Okay.
So my point was that you cannot give me any example of two vectors from R3 such that their addition does not lie in R3. I give you open challenge for that. Okay. It's open to everyone. If I lose, Nishan will pay you 5,000 rupees.
Sure.
See, he trusts me. So, can anyone give me any such example? Two vectors in R3, when added, does not give you a vector in R3. Anyone?
What Chetan is asking would cost way more than 5,000. Basically talking about a wormhole to a different parallel universe. Anyways, let's not go there.
Right. The discussion is a wormhole in itself.
Anyways.
So yeah, and it satisfies scalar multiplication as well. Any vector you take, you multiply it with any scalar quantity. The resulting vector is always going to lie in the vector space R3. You'll find the resultant vector in R3. Okay. So we can call R3 a vector space. If you guys want, you can go through the rest of the 8 axioms as well. But if you guys trust me, I assure you that all of those 8 axioms are satisfied as well.
I must give one example,
Mhm.
It is like, for example, if you have a worm on a worm, which, which is moving on a ground, which is having no wings, whatever path it may take, it can never, ever kind of climb a wall. Of course, walls are not connected with the dish I'm talking about.
Yeah. So
Whatever path, how much effort does it may make, it cannot climb the wall.
Right.
Chetan is saying exactly that.
Yeah, that's a pretty good example for a vector space in R2. That's a pretty good.
That was an example in R2, of course.
Yeah. So you can generalize that for R3 as well. Okay.
Not why
So-
R3, generalize it for Rn.
Yeah, you can generalize it for Rn as well. So okay. So since vector R3 is a vector space, we have confirmed that it's a vector space in itself. Let's move on to the next question. Let's look at the next question. What does the next question say? So the next question says that consider the 2 points 1, 2, 3, 4, 5, 7. Okay. What does the following set denote? Alpha times of 1, 2, 3 plus beta times of 4, 5, 7. Is this a subspace? Interesting question. Okay. Interesting question. Can anyone tell us? See, you can do the same thing, just like how we built this story for subspaces in R2, you can do the same thing for R3 as well. So can anyone tell me alpha times of 1, 2, 3 plus beta times of 5, 6, 5, 4, 5, 7? Is this a subspace? Alpha times of 1, 2, 3 plus beta times of 4, 5, 7. Can anyone tell me? Is this a subspace? Chitura says yes. Anyone else? Is this a subspace? Yeah, Nagashi, you're saying something? Your voice is
Very
breaking it.
faint.
Yeah,
Very
very
faint
faint.
as well.
I said I think it might be a
Okay.
Can you repeat, Chetan?
I think she said that it's a subspace.
Okay.
But
Reason, what is the reason behind it?
yeah,
It's
maybe
a sub-
Nagashri, can you type in the chat because your voice is very faint and it's breaking as well.
Maybe Chitturaja can also type in.
Yeah,
Why
Chitturaja,
he thinks this is a subspace?
right. Or maybe Chitturaja, if you can, yes, it is a subspace. Okay. Maybe Chitturaja, can you unmute and tell us why do you think it's a subspace? Or maybe you can type in the chat. That works as well. It satisfies all the three conditions. Okay. Does it now? Let's see. Does it have an origin in itself? So if we put alpha as 0 and beta as 0, what are we going to get? Alpha times 1, 2,
Get
3
0,
plus beta times 4,
0.
5. It gives me 0, 0, 0. Oh, interesting. It does have origin. Okay. What about if I take any two vectors from these two and add them? Say I have 2 times of 1, 2, 3 plus 3 times of 4, or say 1 times of 4, 5, 7. I think this is going to satisfy both vector addition and scalar multiplication since we are going to multiply some scalar quantity and adding them as well. So 2, 1, 2 times 1, 2, 3 plus 1 times of 4, 5, 7. It gives me a point 6, 9, 13. Does it lie in this set? Does it lie in the set? Does it lie in the set, guys? We are checking both conditions here, vector addition and scalar multiplication. I want to know whether 6, 9, 13 lie in vector lie in this set, this subspace subset. Chittura says yes. I'm not. Oh, I'm not convinced. I am not convinced, guys. I don't believe that 6, 9, 13 lies in this subset. Okay, I don't believe it. Vinay, can you show me that if it lies in this subset or not? Maybe if I see it with my own eyes, I'll believe it. We'll have to move to 3D. 3D. So 1, 2, 3, and 4, 5, 7, and linear combination of that. First, show the trace of the resultant and then plot the plane afterwards. See, guys, what are we getting after the linear combination of these two? These two vectors. Let's see. We'll see what we are getting. Okay. I don't know what we are going to get. We'll see. I have no idea. Can we vary the values, of A and B? Oh, interesting. It's making something. Can you change the speed as well for the values? Perfect. 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 What are we getting here? Hmm? Can anyone tell me what are we getting here? What is this? A plane. Right. So you are telling me that the linear combination of these two vectors is giving me a plane. Interesting. Very interesting. I wasn't aware that it was giving me a plane. Now that I can see, okay, I believe it is giving me a plane. But I still don't believe that vector 6, 9, 11, I think it was, that lies on this plane. I don't believe it. Okay, can you plot this plane, Vinay? Plane of 1, 0, 0, 0, 0, 0, 0, 1, 2, 3, and 4, 5, 7. Perfect. Yeah. Can you remove the trace? Can you remove the trace? What happened? Okay, perfect. Oh, no issues. It is giving you the same plane. Right. Can you guys look at that? Those two vectors lie on this plane? But I don't think the resultant vector was lying on that plane. Can you plot that vector, Vinay? What was that vector? Can you take a look at that vector? What was that vector? Okay, Vinay is confirming. Okay, he wants to see it from every angle. He wants to see. Yeah. So 6, 9, 13. Does the resultant lie on this on this plane or not? Oh, okay. It's lying on this plane. Okay. Okay. Maybe I was wrong, guys. Maybe I was wrong. We are getting a vector on this plane. Now I'm convinced. Okay, now I'm convinced with you guys. Okay, perfect. So we saw that we can get any linear combination of these vectors and that will lie in this set. So now can we call this a subspace of R3? Can we now call this a subspace of R3? We saw that we can get an origin. We saw that it satisfies vector addition. We also saw it satisfies scalar multiplication, right? So can we call this a subspace of R3?
Can
Guys?
I elaborate a bit on this?
Yeah, go ahead.
So when we have 1 point, we have 1 point. When we have 2 points and we connect those 2 points, what it becomes? A line. Is it? Isn't it? So what if we have two lines or two vectors to say? So what is common in those two vectors? If we connect those two vectors, it will form a plane, won't it? So the interesting thing is that whenever we are kind of taking a linear combination of those two vectors, alpha times that vector, a vector A and beta times a vector B, we are getting the resultant on that plane itself. That was formed by those two vectors. This is the interesting thing. For example, we have taken two vectors in R3 plane. The resultant could have, you may think that, okay, there is a point in some random point in the space, in 3D space, and there is yet another point in 3D space. We are adding them. The resultant addition may be anywhere in the 3D space. This could be our intuition, but there is a specific pattern which we could see here. Is that the resultant vector is on the same plane that is spanned by these two vectors. Yeah, that's it.
Right. And we observed that as well. Visually, we observed that the linear combination of these two vectors was giving us a plane, and the resultant vector, when we took a linear combination, was also lying on that plane. We visually observed that. We verified that, and like Nishan very beautifully explained, that verbally as well. So we saw it verbally, we saw it visually, and we heard it verbally as well.
Mathematically as well.
Right. Mathematically as well, right. Okay.
But
So,
why, why not another, why not any other point in 3D space? Why only this plane that is being spanned by these two vectors is the question.
okay, maybe for that we need a bit more intuition for another concept. We'll come to that as well.
Okay.
For that we still need some more things.
Yep.
But okay, but we are done with this question. Okay, we are done with this question. We saw that we had two vectors in R3. We were taking the linear combination of that. We saw that this was giving us a plane. And we observed that plane was satisfying all the three conditions that a subspace must satisfy. So we can call this a subspace now safely. So we conclude that, okay, this set is a subspace. Okay, S is a subspace. Now, can we look at the next question, Vinay? Yeah. Maybe you can highlight this as well. Yeah. Perfect. So here we have the next question, that is, consider a straight line y equals to 2x plus 1 in R2. Does it form a subspace of R2? We need R2 again. R2. Right. Y equals to 2x plus 1. Is this a subspace, guys? Very interesting question.
Doesn't contain 0.
Right. So Devasmith says that it does not cut at 0. So he says it's not a subspace. Can anyone else maybe counter him, or does anyone else support him? Guys? Anyone? Can we call this a subspace? Can we call this line a subspace? Y equals to 2x plus 1. Praneeth, Ravi, Nagashri, Chittu, Bharat, Rishabh, Maria, anyone? Okay, Chittu says no. We can't call it a subspace. Why? Why, Chittu Raja? Why can't we call it a subspace? Guys? It does not contain origin. It does not pass through it. Oh, that's for the very first condition is okay. Ravi says origin is not satisfied, right? So that's what Devasmith said, was also saying, that no origin due to constant. Yeah, correct. It does not even satisfy the first condition, origin. We don't even need to check the other, vector addition and scalar multiplication. And even if you do that, you won't satisfy those conditions. So we can safely say this is not a subspace of R2, right?
Can you
And
relate this with nice function?
yeah. So you remember now we had nice functions, right? We had nice functions. We defined nice functions as functions of the form ax plus by, and we said we say these functions are nice because they have coefficients as non-zero, but the constant as 0. Now you know why constant being 0 was so important, because we were going to discuss vectors, and vectors, they do not pass through any other point except origin. All the vectors, they pass through origin. You cannot give me any vector in linear algebra that does not pass through origin. Okay, so that's why we called them nice functions. They were satisfying those two conditions, scalar multiplication and vector addition. They were nice, very nicely behaved functions. They were passing through the origin. They were satisfying those two conditions. That's why we call them nice functions. I'm pretty sure in the initial stage that term did not make sense to anyone. Why are we calling these nice functions? What's so nice about them? Now can you see what was the nice thing about it? Okay, so those functions were satisfying those conditions. That means those functions can be considered as subspaces. That was nice about them. That was what was nice about them. So if you do 0 times u, it gives you 0 comma 0. But does that lie on this line? It does not, right? It does not lie on this line. So you see that we cannot call it a subspace apart. Okay, perfect. Can we move on to the next question, Vinay? Perfect. So consider a unit circle in R2 centered at origin. Is it a subspace of R2? Very interesting question. Can you show the GeoGebra, Vinay? Can you do x square plus y square equals to 1? X square plus y square equals to 1. Right. Can anyone tell me, is this a subspace? Is this a subspace? Anyone? This is a unit circle.
See, first of all, origin is not condition
The-
1. Condition 2 is any scalar multiplication of vector also doesn't lie on the circle.
Okay, so what if I give you the entire area in this circle as well? That I'm not giving you the circumference only, I'm giving you everything inside it as well. Can we then call it a subspace? Now that will include the origin.
And the radius is still 1?
Yeah, radius is still 1.
Well, I mean, I take two vectors, origin to like 1, 0, and then 0, 1, and then we know it will resultant will be a 0 square root of 2, which will be outside that area.
Right. It will be 1, 1, right? And the magnitude of that is going to be square root of non-linear, right? So
root 2 basically.
root. Axioms will fail. Right. Correct, Rishabh. Axioms are going to fail. I cannot call this circle a subspace. I cannot call this circle a subspace because if I take any two vectors from this circle and if I add those two vectors, I get a vector that does not lie in this circle. It fails the first condition. Even if you include all the points, so right now it's not including the origin, but even if you take all the points inside it, even then it does not satisfy the condition for being a subspace. Okay, it will, the moment you add two vectors, they'll give you a vector outside this, and the moment you multiply some scalar quantity with a vector in this, say I'm taking a vector from this, and I'm multiplying two with that. You see, I'm getting a vector that's outside the circle, that lies outside the circle, that does not even lie in the circle. So if it does not lie in the circle, I cannot call. Can I call the circle a subspace? Can I even do that? Can I call that? Can I call this circle a subspace now? We see that it's failing the axioms. I cannot, right? I cannot call this circle a subspace. So, okay, what if I take, instead of a circle, I'm taking an octagon. Okay, I am a fan of MMA. So I'm pretty sure if some of you are fans of MMA, you know what octagon is. So what if I take an octagon? Will that be a subspace? Devasmith says no. He's nodding.
Because you take there are 8 edges. Let's take a vector connecting edge 1 and edge 2, right? So if you add up, create a number, it will go outside. So
right.
So that's the
Correct.
challenge.
Correct. What if I take a square? What happens then?
Same thing.
Same thing, right? So can we conclude? We're observing a very interesting thing here. Okay, that any shape that's closed cannot be a subspace. Very interesting observation. Very interesting observation. See, our plane is not closed. It goes from infinity to minus infinity. Our lines are not closed. Goes from infinity to minus infinity. But any closed space cannot be a subspace. So that is the very important observation here. That is the most important observation that we make in this question. That any closed space cannot be a subspace. And since it cannot be a subspace, we can't we don't even need to talk about whether it's a vector space or okay. Okay, let's move to the next question. We are done with question number 13. Let's move to question number 14. What are all the subspaces of R2? Now this is very interesting. We have already answered this, but I want someone to quickly tell me what are all the subspaces of R2.
R3, R4 up to Rn. The Volk inverse.
Can anyone tell me what are the possible subspaces of R2? Guys, Praneeth, Nagashri, Chitturaya, Bharat, Anurag.
Linear combination of 0, 1, 1, 0.
0, 1 and 1, 0. Any linear combination of that. Yeah, right. But what are the possible subspaces? You're correct in that. But if we talk about from the very basics,
Let us. She has given right answer.
yeah,
What
that is right.
what are all the
But
what
the
are the
linear
all
combination, no, just
what the linear combination of what she has suggested constitute from?
yeah, right, correct. See, the linear combination of 1, 0 and 0, 1 will give you only one such possible subspace of R2. That is the R2 itself. But there are other subspaces in R2 as well.
0, 0 is 1.
Can you repeat that? Can you write down in the chat, Nagashri? Your
She's
voice is
saying
breaking
that
and it's very faint.
0, 0 is one of them.
0, 0 is one of them, correct? That's one. Origin is one.
Mhm.
Bharat says line passing through origin and plane passing through origin. Bharat, we are only talking about R2, so we only have one plane, that is R2 itself. So all the lines passing through origin and the R2 itself, that is what Nagashri was talking about, that the linear combination of 1, 0 and 0, 1 gives you the entire R2.
Yeah.
Okay, so those are all the possible subspaces of R2. And we discussed this as well. We saw it, right? We first started with the origin, then we got a line when we included Vinay's favorite point. Then we got a plane, the entire R2, when we included Maria's favorite point. So we saw that, we observed that, we saw that mathematically, we saw that visually when we noticed everything in GeoGebra as well. Okay. Now let's move on to question number 15. What does question number 15 say? What are all the possible subspaces of R3? What are all the subspaces of R3? This is very related question. Anyone? What are all the Yeah, go ahead, Nagashri.
The origin.
Right, the origin. We always start from the origin, correct? That's one.
And then any plane that passes through 0, 0, 0.
Right. All planes passing through 0, 0, 0. What else?
And maybe the lines also that pass through 0, 0, 0.
Right. All the lines passing through origin as well. What else?
Why are you asking what else? This will maybe all the cases will maybe over by now. How do you
Are
know
you
what
sure?
else?
Are you sure?
Nagashiri would answer, no?
Is there something else left? Or are these all?
Subspaces, maybe defined subspaces. And then
Chittu
try
Raja
again.
says, I don't know how to define R3 itself. Origin lines passing through origin. Yeah, I mean, okay, we'll talk about it. How to define R3. We'll talk about it.
terms of the linear combination can be the linear combination of 1 0 0, 0 1 0, and 0 0 1.
Correct. That's true. That is true.
Great.
So if you want to define R3 like the way we have defined till this point, you can think of it as linear combination of three vectors. This is 1 0 0, 0 1 0, and 0 0 1. Okay, alpha times of 1 0 0, beta times of 0 1 0, and gamma times of 0 0 1. And it need not be only these three vectors. You can take any three independent vectors. Now we have not discussed the term independence. That's why I did not give this example. But I just wanted to know at this point that you can take any other vectors as well that are linearly independent, not just these three. These are not unique in that sense. We'll be discussing what is independence as well when we come to that. So, okay. So from what I am understanding, what I am getting is that there are four possible subspaces of R3. Origin, all the lines passing through the origin, all the planes passing through the origin, and the R3 itself. So can we generalize this idea to Rn? Interesting question, right? We observed what were the subspaces of R2, origin, all the lines passing through origin, and R2 itself. We observed what are the subspaces of R3, origin, all the lines passing through origin, all the planes passing through origin, and R3 itself, entire R3. Can we now generalize this to Rn? Can anyone tell me what are the possible subspaces of Rn? Anyone?
The origin,
Right?
then R2, R3, all of them are subspaces of Rn until R minus 1.
Correct.
So
Why R minus 1, Rn minus 1? Why not Rn?
Rn is also a subspace.
Right. So from Rn, we have everything till origin. That is Rn minus 1, Rn minus 2, Rn minus 3, and so on till origin, right? Right. Rishabh says the same thing. That Rn minus 1, R3, R2. Rishabh, will we not have Rn itself?
Yes, we will be having
Yeah.
R also.
Correct. So Rn minus 1, Rn minus 2, 3, and so on till the origin. We will have everything in between. So we generalize this idea to Rn. As Nishan always says that math is all about observing patterns. We observed pattern what was happening in R2, and we observed what happens in R3, and we generalize this to Rn. Okay. So yeah, it's time to treat hyperplanes. Right. So let's just look at the next point as well. So so the next question is question number 16. Given R3, pick any 2 points u comma v that belong to R3. Note that alpha times u plus beta times v is a subspace of R3. Generalize this idea. Okay. So sir says that pick any 2 points, any two vectors in R3. I need your favorite vectors now, guys. Pull out your favorite vectors. Tell me your favorite vectors. I need 2 such favorite vectors.
1 second, Chetan. So what did the okay, Srivan has deleted that. Okay. Let us delete it afterwards.
What happened? Were you pointing towards something? Did I miss something? Nishan? Hello?
Srivan is writing.
Yeah,
I think he wants to talk about hyperplanes.
Yep.
Okay, yeah, you can go ahead.
No, I was saying that should we mention hyperplane here or not?
If you want to mention, you can.
See, of course, if we are talking about subspaces of nth dimension, or that is to say Rn, as the generalization goes, that okay, 0, 0, that is to say origin is one of the subspace. All the lines passing through the origin is a subspace, and all the planes passing through the origin in a subspace, and all hyperplanes and R3 passing through origin belongs to the subspace. All hyperplanes in R4 passing through origin belongs to the subspace, and so on.
Right.
So what do we mean by hyperplanes here is the question. It's kind of I have not explained anything. I have just given kind of a statement, a generalizing statements, just looking at the pattern. I've seen, okay, 1 + 1 is 2. So I kind of predicted, okay, 1 + 1 + 1 is 3. But why? Not why. What is this new term, hyperplane?
Yeah. I think hyperplanes are best understood from R3 to R4. Right? We can all visualize R3, and it's quite easy to talk about R3. R3 itself is a hyperplane because it is made up of multiple planes of R2, right? You can always break down the entire R2 as take a plane and move it along another direction. This plane was moving only in 2 directions, right? That plane was found by moving in 2 directions. When I add the third direction and I move up and down, I kind of make a cube, right? That cube is what we call R3. And we can visualize R3, right? That's helpful for us. But when we talk about anything above R3, which we're not able to visualize, it's like taking R3 and moving it in a new direction, right? That's what we call R4, right? We say time is R4, right? For us in our world, we say the time. So it's like we're moving in across a new dimension, moving a cube across a new dimension. There are multiple cubes making up R4, right? So that we can call any dimensional object.
So if you want a formal definition for a hyperplane, the mathematical or the bookish definition of a hyperplane is any subspace, okay, of nth, n minus 1th dimension. Okay, so you have Rn, all such subspaces that have Rn minus 1 dimension are your hyperplane. Okay.
That was top-down approach. I'll just give a bottom-up approach as Srivinay just gave actually. So it's like if you kind of take a point, fine, and try to plot it as we were just trying to plot them on GeoGebra. What do we call them? A very nice thing that is called, we kind of not plot, trace them.
Right.
We take a point, we trace it, where all it's going. What do we get? If that point is kind of moving in a straight line, we'll get a straight line eventually. For example, x is equal to y. Fine. We are going to take points along this line. When we are going to trace this point along this line, what it's going to trace? It's going to trace a line eventually. Locus. Now I get the point thing. Locus. Oftenly we have seen during our school days that geometrical figures are kind of explained with the help of locus. Fine. And locus includes tracing points where a point can reach. We are going to drop a dot on the paper wheresoever that point can reach, and eventually a geometrical figure comes up, and we say, okay, this is the locus of a circle, this is the locus of a straight line, and so on. And eventually we write an equation related to that. So what do we get when we kind of trace points? We get lines. Fine. What if we are going to take locus of a plane? I mean, let us take a plane passing through origin, one plane. Let us tilt the angle of that plane by a bit, by alpha angle, and keep doing it. Keep varying alpha randomly, keep doing it, and make locus out of it. Make a trace out of it. What eventually we are going to make? We are going to make up a cube. That is what we call R3 plane. Up till now, it was very much easy for us to imagine. Okay. See, we made a trace out of a point. We got a line, and we made a trace out of lines, and we got a plane, and we made a trace out of planes, and we got a cube or R3 plane or R3 space. What if we move from R3 to R4? What if we are going to make trace out of R3 space itself? What are we going to get? The thing is that it's beyond our imagination. So we start talking about hyperplanes. We cannot call it what we just previously explained, a cube. We cannot say the cube has a finite space. We cannot say cube to be cube is not an appropriate word to say. We use it just to for our convenience to explain R3 space. Okay, it's kind of cube. Anyways, so what basically the case is, anything after a plane, anything that a plane traces, as we move up the dimension, as we were kind of moved from point to line to space, and then we start calling it hyperspace. Sorry, hyperspace, I'm hyperplane. Anything above plane. So we had points, we had then lines, we then have planes. So what after that? Planes are in R2 plane. Planes are in second dimension, that is in R2 or R3. We have lines in R2. Okay, R2 itself makes a plane. Anyways, let's not go in there. The thing is that what I was telling that, okay, the R2, the planes, hyperplanes, which we are going to get out of many planes in different dimensions. We start calling it, and okay, we have got a hyperplane in R3 dimension. We have got a hyperplane in R4 dimension. We have got a hyperplane in R5 dimension, and so on. Because we do not have any specific name for after planes. What we call something after plane. So the generalization, see the sequence, see the chronology, from 0, 0 to a point, to line, to planes. What after that? Hyperplanes. Hyperplanes in R3, hyperplanes in R4, hyperplanes in R5. So when we talk about subspaces of Rn dimension, what are they? 0, 0, 0, 0, 0, 0. That is to say origin. Then all the lines passing through the origin. What after that? All the planes passing through the origin. Okay, we are in 3 dimension presently. What after that? After that, we will start saying that all the hyperplanes in nth dimension passing through the origin. And another dimension could be R4, R5, R6, up to Rn. All the hyperplanes will be a subspace of it. So when we talk about, subspaces, this concept of hyperplanes must be kind of understood. This is what I was saying. Yes, Chetan.
Okay. So thank you,
If
Nishant, for that.
if anyone is not clear with what we just talked about, you just cross question, and we'll just try to make your concepts pretty much clear.
See, by definition, what happens is we introduce this idea of hyperplanes because our imagination is limited to only three-dimensional space. Like Nishan was talking about that worm, right? It was moving in two-dimensional space. It can't climb in on a wall. That was three-dimensional. So it was limited to that two dimensions, right? Its imagination was limited to two dimensions. It cannot think of flying. So similarly, we are limited to three dimensions as well. We cannot think beyond three dimensions. We cannot even imagine beyond three dimensions. So that's where the idea of hyperplanes becomes necessary. By definition, a hyperplane is just this. If you have a space of n dimension, all all planes or all such subspaces of Rn minus one dimension are your hyperplanes for that. Okay. That's like the bookish definition of it. And we introduce the definition because we are not able to imagine beyond three dimensions. So that is the whole idea of hyperplanes. Yeah. Can we look at the next question, Vinay? Yeah, perfect. So the idea of hyperplanes was very beautifully explained by Nishant. I hope it's clear to everyone. If you guys have any doubts, you can ask before we move on to the next question. Anyone? Rishabh says anything above R3 is a hyperplane. No, Rishabh, I think hyperplane also includes everything inside below R3 below R3 as well.
Just call it R3,
Okay.
a hyperplane in that dimension.
Right.
For example,
R3,
we can call hyperplane in R3 dimension.
yeah. So all the planes in R3 are actually hyperplanes of R3.
Because kind of we are what we said, it is, as I said, it is not appropriate to consider kind of imagine a plane to be a cube. Fine. So we cannot say that a cube is a plane. Okay, so it was just for the sake of imagination, so that we can imagine. We kind of say, okay, what a combination of all the planes passing through origin constitute. So as Chittu Raja was kind of giving a statement that okay, it'll form a sphere. So he kind of imagined this to be a sphere. Fine. So somebody would say, I imagine it to be a cube. Somebody would say, okay, my plane is not a square. My plane is rectangle. I imagine it to be a cuboid. Anyways, so the more appropriate thing would be to call it a hyperplane in R3 dimension. That is the most appropriate thing
See,
we can.
when we look at the visualization, right, for GeoGebra, let's say, when we think of a plane, we think of it as a rectangular object, but it is not a rectangular object. It's for our visualization that GeoGebra shows it as a rectangular object. But in all reality, it spans from infinity to minus infinity. It goes from infinity to minus infinity. We don't know any shape for it. There is nothing we know about it, about the shape of it. Okay, so we think of it as some closed object. We call it a square, we call it a rectangle, we call it a sphere, octagon, or any polygon. We think of it as that. But the idea is that it's an hyperplane in R3. We don't know anything about its limits. Okay, we only know it goes from infinity to minus infinity. That was the whole idea of hyperplane. Okay,
Chetan, so I'm not sure. This point also can be called a zero dimension hyperplane.
Yeah, if you want to call it a hyperplane, you'll call it a hyperplane in R1. So by definition, any subspace of a space in nth dimension, any Rn minus one subspace. So if we are in say R1, Rn minus one will be R0, right? So any point will be a hyperplane of that. See, you don't know the shape of the point, right? There is no shape. By definition, a point does not have any height, does not have any length, right? If it has some length, it will become a R1. It will not remain R0. So anything that is not imaginable, we introduce the idea of hyperplanes for those. Yeah. Okay. Let's move on to the next question, guys. I hope it's clear to everyone. If it's not, you can type in the chat. I'll take a look in the chat. So we did question number 16, right? Okay. The set alpha times of u, that's question number 17. The set alpha times of u plus beta times of v is called the linear combination of vectors u and v. We can generalize this to k vectors. Observe what this set is all about, right? So sir says that okay, you took the linear combination of two vectors, u and v. What happens when you add more to that? Can we go to GeoGebra, Vinay? Can we go to that graph we made for the span of those two vectors? Yeah, perfect. Now I want to take another vector. Okay, I want to take another vector. Can anyone give me another vector that does not lie on this plane? I want another vector that does not lie on this plane. Any of your favorite vectors? Right? Okay, Vinay has put his favorite. So you'll have to increase the size of that, I guess, Make it 3 or 4, so that yeah, perfect. So Vinay gave me a vector that does not lie on the screen. Can you see that it does not lie on the screen, guys? Right? It's visible. Now it's visible that it does not lie on this. Okay, let's take the linear combination of all these three vectors. Let's see what we get. Let's trace the resultant of that. So let's do a times u plus b times v plus c times d times c. D times c. It will not work there. We'll have to create yeah, yeah, perfect, perfect. Just do okay. Create another some variable or make b times v plus d times c. Perfect, perfect. Now, can you just turn on the trace for the resultant and just change the color of it so that we can visualize it better? Any color, any color. Okay. So now we are tracing this linear combination. Can anyone tell me what are we observing here? Should we be getting this in it? Can you change the vector itself? Or are we changing everything? Can you make the
Yeah, I think
uh
the step size for D is very small.
yeah, I think that's the reason. Chittura says I'm seeing a plane, right? That's what I'm looking at as well. Shouldn't be the case. I mean, still
This is the locus we were talking about. That locus that gets traced out of a line,
No,
out of
no,
a
no.
plane, and
Yeah,
many
right. But
things.
I was hoping for something else. Can we change the vector, Vinay? Maybe take -1, 2, 1. -2, 1, or -1, 2, 1.
Sorry, 1 second. So what do you want?
-1, 2, 1. Change the vector C to -1, 2, 1. No, no. Vector inside the bracket you will have to change.
Why?
Yeah.
What happened?
It's not giving us the what we want you to see.
Okay. That's so. Hmm. Yeah, maybe we can't see it clearly.
Can you just change the vector, make it -1, 2, 1. -1, 2, 1. Yeah. Perfect.
Let
Now
me
can
change.
you zoom out? Can you zoom out? Right, right, right. Perfect, 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 perfect. Now it's giving me the, just change the speed as well, just increase the speed so that it spans everything quickly. Right. Can you guys look at it and can you guys tell me what are we getting here? What are we getting here? Can you move this around, Vinay? See, what are we getting here? Does this look like a plane to you, guys?
Pretty.
Does this look like a plane to you? No, Chitturaja says no. It does not look like a plane to him. Okay, that means we are getting some vectors in different directions, in other than two directions as well. Don't know the shape of it. Yeah, I don't know the shape of it as well. But what we need to observe is that now we are getting uh, vectors in more than two dimensions. We are getting vectors in three dimensions now. They're not confined to a plane. They're not confined to R2 itself. Now they are lying in three dimensions. So if we can get any vector in three dimensions, we can obviously get all the vectors along that same line, right? What we are observing here is the moment we added a third vector, we spanned the entire R3. We got the entire R3. Okay, that was the observation here. Now, can we generalize this idea to some k vectors? Can anyone tell me if I take more than three vectors, say five vectors, what am I going to get? All of them lying in R3. We'll come to higher dimensions as well, but right now let's why it was not like this when we gave 5 comma 0. Yeah, I'll focus on that point as well. I'll focus on that point as well. But before that, can anyone tell me what happens when we take more than three vectors in R3? Chitturaja, this point is actually connected to the question you're asking. We'll focus on that as well. Can anyone tell me what if I take five vectors from R3 and take the linear combination of those five vectors? What am I going to get? Praneeth, Nagashri, Chitturaja, it will span the entire R3. Oh, interesting. You're saying that if I get three vectors, I'll span the R3. If I get five vectors, again I'll span the R3. Okay, interesting. Right, right, right. That is right. Correct. But we observed something there. Very interesting observation we made. We took the
Wait.
point 5 comma. Mhm,
No, I'm a little confused.
mhm,
So wait. Okay, this idea I've understood. In question number 16, we said if I take any two vectors, u comma v,
mhm.
alpha times u plus beta times v is a subspace of R3, right? Did we
Right.
generalize this idea? Not
Uh,
really sure.
Pick any 2 points is a subspace of R3. Generalize this idea. Yeah, I mean, even if we change the vectors, we will get a plane, right?
No. What if I take u to be 1, 2?
No. We both are okay. Yeah, we're actually touching upon that as well. That's
I
the
think that's
reason we
what
got.
we should have touched about.
Yeah. I think. Okay, let's think about it. Let's think about it. Why did we not get uh uh R3 when we took 5 comma 0 comma 0? Is it true that when we take the linear combination of any two vectors in R2, we get a plane? Sorry, any two vectors in R3, we get a plane. Is that true? I think this is where the idea of we should have introduced that idea in question number 16. Yeah, anyway, we'll introduce it right now. Two independent vectors, right, correct. What are independent vectors? What are independent vectors? Can anyone tell me what are independent vectors?
Let's not go there. I mean, we'll understand what independent vectors are, I think, as we solve the questions. Like I think question number 18 is about that. Or
Just a second. Okay. Let's do one thing. Can we go to GeoGebra? Let's not talk about independent vectors. Let's observe what happens.
Yeah.
Okay. Can we go to GeoGebra in 2D?
Mhm.
We have opened 2D, right? We already have one opened. Right. Yeah. So let's take one vector here, 1 comma 2, Vinay's favorite point. Let's take another vector, 5 comma 12, Maria's favorite point. Let's take the linear combination of these and trace that. Let's see what we get.
We already did that, right?
Yeah, let's just do it one time. Let's see what happens. We're going to trace it. Okay, perfect. Yeah. So let's see what happens now. What are we observing here? We are observing that we are going to span the entire R2. We are going to get every point on R2 itself, right? Okay, now Vinay included his favorite point, Maria included her favorite point. I want to include my favorite point as well. 3 comma 6. I want 3 comma 6. Now I want to see what am I going to get if I have 1 comma 2 and 3 comma 6. Let's see. Oh, interesting. Very interesting. We're getting a line now. Earlier we were getting a plane, now we are getting a line. Why? Why? I think why? Okay, let's see. Maybe it's happening in R2. Maybe it's happening in R2. Let's check in R3 as well. Okay,
But
let's.
but before that, we still see that even okay. I just took two vectors and I took the linear combination of them, which is alpha times u plus beta times v, and we realized in one case it made the entire plane, right? And we know the entire R2 is a subspace of R2. In case two, we created a line, and we know that also is a subspace of R2. And if I happen to, if u and v happen to be 0, 0, right? What if u and v happen to be 0, 0? Then
I'm going to get.
a point 0, 0, and that's only, I mean, that itself is a subspace, right? So whatever linear combination I take of any two vectors on R2, doesn't matter what two vectors, right? There are differences between some cases where 0, 0, if the two vectors happen to be 0, 0, I get only a point. But I know that that point will still be a subspace of R2. If I take a linear combination of 1, 2, and 3, 6, like we did, we were getting a line, and that line was passing through the origin. So we know that's a subspace. Subspace of R2. Is it 12 a.m.? Okay, wow. That's all.
Oh yeah, yeah.
So
It is true.
who's automated reply? Okay.
Mine. I should get a break. I should catch a break for a while.
Yeah, yeah, yeah. Please do, please do.
No,
Please
I'll
do.
finish the explanation though. Yeah. So I think the main thing that we realize is whatever two vectors we take and we take the linear combination of them, it creates a subspace, right? And linear combinations are nothing but nice functions, right? We saw that there's no constant value. There's only a scaling of one value and adding it to the other value, where we don't have any constant in that. Yeah, so we can also generalize this to R3.
Right.
Do you want to share your screen for a minute?
Yeah, yeah. Right.
Or all of us can take a break. It's
Okay, yeah.
Maybe
whatever.
We started at
maybe
9.
be done with this 75
Yeah.
questions for the day. Maybe.
Yeah.
Okay,
I feel it's
okay.
not good.
Okay, let me just stop the recording. I think we can conclude today's sessions now. We'll pick up from here. We'll talk about this idea tomorrow. We'll continue from here.
Up to which question we have discussed, Chetan?
Question number 17.
Okay.
But there is one, the idea of linear combination we have to stress upon before we move to question number 18.
Oh, fine.
Yeah. Okay, guys, thanks for joining, and we'll continue from here tomorrow.